My name is Iqbal Khan. I'm a technology evangelist at Alachisoft. We are a software company based in San Francisco Bay Area. I'm personally based in Tampa. But we have this product called Encache. It's a .NET distributed cache. Today I'm going to talk about how you can scale .NET applications with distributed caching. This is not a talk about Encache. It's about the problem of scalability and how you can resolve it with distributed caching. What should you do? How should you use it? What are some of the best practices? If you have any questions, please feel free to stop me so that we can have more interactive discussion. Okay, let me get started. So let's get a few definitions out of the way. Number one is scalability. Scalability is not performance. You may have an application that performs really well with 5 users, but it is only scalable if it's going to perform the same way with 5,000 or 50,000 or 500,000 users. So scalability is really high performance under peak loads. If your application is not performing well in 5 users, then you need to attend some other talks. Linear scalability is more of application deployment concept. When you deploy your application, if you can add more servers to the deployment, and by adding more servers, if you can increase the transaction capacity in a linear fashion, then your application architecture is linearly scalable. Otherwise, it is non-linear scalable. What that means is that after a certain number of servers, adding more servers actually makes matters worse. That means there are some bottlenecks somewhere in your application which are not being resolved just by adding more servers. So you definitely don't want non-linear scalability, and you definitely want linear scalability in your application. What type of applications need scalability? These are ASP.NET applications. These are web services. These are IoT backend, which are again mostly web services. These are big data processing applications, which are not that common in .NET. More and more of them are being done in Java, but nonetheless, these are the applications that also need scalability. And any other server application. For example, you may be working for a large bank that has millions of customers, and customers call in to make address changes, or maybe they want a new card issued, or maybe they're transferring funds from one account to the other. And all of those transactions need to be processed within some predetermined time frame for compliance purposes. So you again have to handle millions of requests within a time frame that you may not be able to do from a single computer. So you need to be able to scale even in that case. So if you have any of these applications that need scalability, then this is the right talk that you've come to. So let's define the scalability problem also. What is the scalability problem? Well, the application tier scales in a linear fashion. You may have a web application, ASP.NET or web services. You'll have a load balancer in front of it, which will route traffic evenly to all the servers. You can add more servers, no problem. Everything works perfectly fine. I was talking to somebody earlier about the database becoming a bottleneck, and they were not agreeing with me. So I think this is a good opportunity to have that discussion. So database itself performs super fast. There's no issue with performance. Databases are very smart. They do a lot of in-memory caching in their own server. But scalability is something that they, by design, cannot achieve, because you can add, for example, you can add 10, 20, 30, 40, 50 servers at this tier. We have customers with 50 or more servers in their application tier because they have so many users. Imagine you're a large bank or you're an airline. You have millions of people who are coming to your website. You've done this major promotion for a ticket to Hawaii or something. Everybody's going to come. They'll do the flight search. They want to buy the tickets. You can add more servers here, no problem. The database was performing super fast. The software is great, but by design, database is not a distributed database. It is kept in one place. Maybe you can have a cluster of 2 servers, active, passive, but they're more for reliability than for scalability, really. So you can't really have 10 servers here. Unless it is a NoSQL database, then you can. But for a relational database, any of them, it could be SQL Server, Oracle, DB2, MySQL, they're super fast. They may be even doing a lot of in-memory processing, but they will become the bottleneck as you need to scale more and more. And basically, when you have 1,000 or more simultaneous or concurrent users, you start to notice performance issues. And as you grow more, from 1 to 5,000, 5 to 10,000, that's where you start to see more. So what we've seen is, if you have 1,000 users, you may or may not use caching, but as you grow to 5,000, 10,000, 15,000 users, you definitely feel the pain, and you end up with these scalability bottlenecks. Now, relational databases or mainframe legacy databases have this problem. It is one of the reasons NoSQL databases movement started was because of that, although it also has other benefits. And we have a product. I'm just going to quickly, just for reference purposes. We also have so we have a caching product, but we also have a NoSQL document database, just like DocumentDB. It's an open source database. So NoSQL database definitely does not have the scalability problems, but it is not always the answer. Why is that? Because for it to be an answer, a NoSQL database wants you to store all the data in it. So unless you store your data in a NoSQL database, which means you stop using relational database for at least that part of the data, it is not going to solve your problem. So in many cases, you can move some of the data, a lot of the data, into a NoSQL database, and that's what's driving the NoSQL movement. But relational databases, legacy mainframe data, they're here to stay. They're not something that you can just wish away for both technical and business reasons. So whatever scalability problems you have to solve them with relational databases in the picture. That's why a NoSQL database is not always the answer. And the way you solve that problem is it's a new best practice that has emerged over the last 5 to 10 years or so, which is the in-memory distributed cache. Some people also call it in-memory data grid. Microsoft used to call it data fabric, although they keep changing their definitions. But it's an in-memory distributed key value store. And it is an essential part of your architecture now. If you want a scalable application, you need to develop your applications with a distributed cache in mind, so that you can make sure that the application will never become a bottleneck. Now, what is a distributed cache? It is essentially 2 or more low-cost servers. These are not high-end database servers. These are web server type of boxes. Usually a dual CPU, a quad, 8-core configuration is pretty typical. 16 gig of RAM is pretty much average. We see 16 to 32 gig is like the sweet spot of memory. More than 64 gig, we don't even recommend to our customers. We say add another box instead of making this box more stronger. Because if you add more than 64 gig, a .NET application has this thing called garbage collector, which takes a lot of processing power. So the more memory you have, the faster the CPU has to be for the garbage collector to be able to collect all that memory. So it is better to have more servers than to have really high-end few servers. Minimum of 2, of course, because you want reliability in case any one server goes down. But then after that, 4-to-1 or 5-to-1 ratio. So usually you would have, let's say, 2, 3, 4, 5 servers in the application tier. The most common we see is between 4 and 10. And then, of course, there are many customers who use more than 10. But 4 and 10 is pretty much what we see as the sweet spot. And for that, you'll use a 2-server cluster. As you grow more than 10 or 12, you add a 3rd one or 4th one, and so on and so forth. And because a distributed cache is a key value store. It's distributed. It replicates data across multiple servers in an intelligent fashion so that you get reliability, but at the same time, you don't spend a lot of time replicating. For example, if every piece of data had to be replicated to all the servers, that's a lot of extra processing that you don't need. So it's that type of intelligent replication that it needs to do. Sometimes you do need to have replication in that way, but those are specialized cases. So a distributed cache, when you have that in place, you will go to it about 80% of the time. All the reads are going to be done from it, and all the updates and some of the reads are going to be done to the database and also to the cache. So if you can trap about 80% of your database traffic to your cache, suddenly your database is very light. It doesn't have a lot to do. So whatever it has to do, it'll do much faster. So performance will improve as well as scalability. This in-memory distributed cache, whether that is Ncache, whether that is Redis on the .NET side, on the Java side, there are more players. Whichever product you choose, distributed cache pretty much is a given best practice now. You have to incorporate this into your architecture. Any questions on this so far before I move on? Okay. Right.
All servers will maintain same copies of cache. So here, like this diagram, you're seeing 5 servers which are maintaining cache. Right. All servers will be maintaining same type of data.
So yes, one logical cache can span multiple servers. In case of Ncache, you can have multiple caches on the same servers. So each cache becomes its own container for isolation purposes. But any one cache can span all 5 servers. And the replication, when I say span, it means some data is on one server, some on the others, And then replication is a separate part of it that may or may not be done depending on your preferences. But yes, all servers are used for storing that cache. And the cache has to be coherent. It has to be always correct. Or, you can say it has to be eventually correct, but pretty close to being always correct. Whatever you store in the cache, if you update, you don't care where the data is. You probably don't even know where the data is. All you know is that this cluster has my data. And whenever I might have stored it from this server, and I'm trying to read it here immediately afterwards, and I should be able to get the same copy. If I can do that, then this becomes a consistent or a coherent cache. So that much data integrity for updates, it always ensures.
So if updates happens, right, you store them first and on the in-memory cache, distribute them across all the servers. When they end up in the database finally?
That is your preference, and I'll go into that in more detail in terms of how you actually use the cache. So one thing that you should, the main goal of up until now is to convince you that if you want scalability, you need to have this as part of your architecture. So now that we've, let's say, agreed that you need a distributed cache, the first question that comes to mind is how do you use it? Where do you use it? What type of, what do you use it for? What data is kept in it? And all the issues related to that data. So there are 3 high-level use cases. Number 1 is the application data caching, which is what I was just talking about, which is you have data in the database, you fetch it, and you cache it. So in the application data caching, the goal is what I just mentioned, that you don't want to go to the database as much. You want to reduce that database traffic so that your application will scale. But the data now exists in 2 places. It exists in the cache and it exists in the database. So whenever data exists in 2 places, what's the first concern that comes to mind? Synchronization between the 2. So is it consistent? Because if the data is not going to be consistent, then you will be limited to using the cache for read-only data. In fact, most people, when you ask them, what do you use a cache for, the knee-jerk reaction is read-only data. I don't feel comfortable using the cache for any data that's going to really change in real time or at runtime. But if you can't use the cache for transactional data, which is what I use that term, for data that changes frequently, that data is probably 80 to 90% of your data. So that means, 80 to 90% of the time you can't even use the cache. And if you can't even use the cache, then it becomes just like a NoSQL database. It's not always the answer. And you want it to be the answer. So so a good distributed cache has to give you the confidence that whatever you cache will be consistent with the database. If it is not, then that cache is not the right cache for you. So that's the first thing, that's the first use case. The second use case is if you have ASP.NET applications, that you can store your sessions in the cache. Sessions are something that almost all ASP.NET applications have. They're either kept in an in-proc mode or in the SQL Server mode. SQL Server is not a right place to keep sessions for two reasons. One, of course, that first reason, which is the more you keep data in the database, the more of a scalability bottleneck you have. The second is that sessions are kept as blobs, and relational databases were not really designed for blobs. They were designed for more structured data that you can index and search. Whereas a distributed cache, the value is a blob always. So these sessions fit in very nicely with a distributed cache. The second type of ASP.NET data is if you're not using the MVC framework, which a lot of the existing ASP.NET applications still aren't, then you have this thing called a view state. And a view state is nothing but an encrypted string that is kept and is sent to the from the web server to the browser, only to come back to the web server. And it can get pretty big. It can be hundreds of kilobytes easily. And so it consumes a lot of extra bandwidth. It takes more time to travel. When you multiply that by millions of requests that you're processing, your bandwidth consumption cost also goes up quite a bit. So it's an ideal case for caching on the server side and only send a small key. So then the next time when the view state is supposed to be used, the key is sent back and the view state is fetched from the cache. The third example of ASP.NET specific caching is page output. It is part of the ASP.NET framework. It's called an output cache, which allows you to cache the output of a page if it's not going to change. And you can use a distributed cache to cache it instead of keeping it in every web server separately, which then becomes multiple copies that need to be synchronized. So these three use cases, or the three examples, are for the ASP.NET specific caching use case. Now, unlike application data caching, here the nature of the problem is very different. Here the data exists only in the cache. I mean, all of this data no longer gets stored anywhere else. So it's not being stored in the database. So you no longer have that synchronization issue between the database and the cache. But you have another issue now. If you have an in-memory cache that's the only store of your data, what's the biggest concern? What could go wrong with that?
It disappears.
Yeah, it can go away. If any one server goes down, and servers do go down, Windows including. So when a server goes down, you lose data, and especially for view state and session state, output cache, sure, even if you lose it, you just re-execute the page. But these two, for example, session state, you just had this airline customer who did all sorts of flight searches, and he's about to place the order, and the server crashes and his session is lost. He has to re-log in. You may lose that customer. So you definitely don't want to lose. So you don't want this data to go away. So in this, synchronization was the big issue. Here it's reliability. So reliability is handled through replication. Any cache that does not do replication, you cannot store sessions in it. The nice thing about the ASP.NET specific caching, by the way, is there's no programming needed. It fits in completely within the ASP.NET framework. Unfortunately, you have to do programming for the application data caching, because on the Java side you don't have to. or actually there are more standards emerging. There's a standard called JCache, which if you program that, then any of the third-party caches just plug into it, and then you don't have to stick to any one cache. Even more so, if you use an OR mapping engine like Hibernate, or in case of .NET and Hibernate, you can plug in a cache. Entity Framework, until the EF Core, or until before EF Core, it did not allow a third-party cache to plug in automatically. Although we had implemented an ADO.NET provider for EF6, that was more of a ADO.NET level caching. So you were caching queries, which is better than not caching, but it's not as powerful as caching at the entity level, where you can also keep track of updates. EF Core, the new EF7 or EF Core, has a much more flexible architecture. It allows you to plug in a third-party cache. So when you move to EF Core, you'll be able to plug in a distributed cache like Ncache without any programming. So you are just doing your standard programming and cache plugs in. But other than that, you have to, but even in that plugin, you can't use all the features that I'll talk about. But in ASP.NET specific, at least, this is the easiest win. When you bring in a cache, since there's no programming involved, you just need to do some basic sanity testing, and your application suddenly sees a major boost in performance and scalability. Any questions before I move on?
Is there any, I don't know if I'm asking right, but for errors or any error handling routines or any messages, if something is out of whack or anything in terms of that extent?
In terms of the application or in terms of the cache?
No, in terms of cache.
Yeah. Well, a cache is just like a database. So just like you make calls to the database, and then you have exception handling. If something goes wrong in the cache will throw an exception. You catch it, and then you have to take the appropriate actions. However, unlike a database where an update can fail on data integrity because you may have check constraints or other referential integrity constraints, none of those constraints exist in the cache. A cache will accept all data that you give it. The only time a cache update or operation will fail is when something goes wrong with the system. Yeah, something catastrophic. So you don't have to worry about the cache not updating your stuff in a normal operation.
Is there any authentication between cache data and servers that use it? Or you configure this server has this URL for cache and no authentication. I ask cache and it don't answer.
So that depends on which cache product you use. Ncache has all of those features built in. You can turn on security so that every user that uses the cache has to be authenticated, authorized. It also has a lot of other security like encryption built in. So if the application that you have is very sensitive, you can encrypt the data before it gets cached. And all of that's just done automatically by the cache without you doing any extra effort. Because as I said, Ncache, one of the biggest users of Ncache is the financial services industry, because they have a lot of online banking, a lot of e-business happens there, and their data is very sensitive. So yes, that depends on which product you pick. The third use case is runtime data sharing through events. Just like you use message queues, MSMQ is one, RabbitMQ is another. Those are they have a lot more features in terms of messaging for a distributed environment in more than one location. If your application is all in one data center and you need to do pub-sub type of data sharing, a distributed cache is much more scalable than any of the message queues. It may not have as many features as they do, but you may not need all those features. But it is much faster and much more scalable. And that is true for Ncache. That is also true for other distributed caches that provide this feature. Because, again, this whole cluster becomes a message bus. So you have, if you're doing a lot of activity, the events propagate very, very quickly because there are more than one server to handle those events. And you can add more servers as the load grows. So a lot of the server applications these days, they have built-in workflows, where one application does something, and once that's done, then other applications do something else. So that's where the pub/sub or the producer-consumer concept comes. There's an event notification features. Encache has this feature called continuous query, which is a very powerful feature, which is also in the Java side it exists, but none of the other .NET caches have it. So runtime data sharing is also something that you should strongly consider doing through a distributed cache. Makes your life much more simpler than instead of incorporating multiple other products. Even here, the nature of the problem is usually the same as this, which is that the data that you're trying to share exists only in the cache. It might exist in the database, but in a different form, because you've constructed it, you've produced it, you've brought a lot of data together, and in this final or intermediate form, you're sharing it with somebody else. So if you lose that data, you have to redo the whole thing. So although it's not as bad as sessions, but it still has a lot of performance implications. So you don't want to lose that data. So again, here the concern is to make sure that the cache is reliable. So those are the three high-level use cases that a distributed cache provides. As I said, a distributed cache is essentially a distributed in-memory database, a key value store. Before I jump into more specifics about how you can do these, I'm just going to quickly show you what a distributed cache looks like so that you can see how it will be if you were to use it in your application. I'm going to, of course, use Encache as the example. Encache is an open source cache, so you can use it without buying it if you don't have the money or you don't have the budget. If your project is more business sensitive, then of course buy the enterprise edition. Let me quickly. So I have where'd it go? So I have set up some VMs in Azure that I'm going to use. I'm going to use a 2-node cache cluster. So I have demo 1 and demo 2 as my cache servers, and demo client is my application server box. So that's your ASP.NET server box. So an Encache client is your application server, really. So I'm logged in. I'm logged into, let's say, demo client. So the first thing I'm going to do is create a new cache. So I'm going to use this tool called Encache Manager. So it's an Explorer style tool. I'm just going to say create a new clustered cache. In Encache, all caches are named. I will pick a storage or a replication strategy. I'm just going to go ahead and specify my first cache server here. Specify my second one. And I'm just going to continue, and I will say, here's how much memory my server should consume. In your case, it's going to be a lot more. I've just specified 1 gig. So then, if that memory is consumed, you can specify eviction policies. So let's say a least recently used policy means evict some of the items that are least recently used. So I've just gotten that. I'm going to go ahead and add a client node, which is my box. And I will just go ahead and start the cache.
So what machine are you setting this up on?
This is in Azure, so these two are my demo 1 and demo. So I'm actually logged into this box, and I'm using Encache Manager here, and I'm creating a cluster of demo 1 and demo 2 here. Oops. So now that I've started this, I can go ahead and I can view statistics. So I can see some perfmon counter activity. I can also launch this monitoring tool of Encache that lets me see things. And then I'm going to just quickly run this tool called stress test tool. It lets quickly test the cache in your environment to see how it's going to operate. So that tool is like your application, so except you can use it to simulate different types of load, different types of operations. So for example, I'm doing about 600 some requests per second here, and about 700 to 800 each. Let me run one more instance of stress test tool right here. So you'll see that load will just double. So as I keep adding more and more instances of the application, the load on the cache will increase until such a point where these two servers are going to max out. And then you just add a third one. And you can do that all at runtime without stopping anything. So suddenly your infrastructure, just think about this. If your database started to choke, can you really add another server and get out of that problem? You can't, because of the nature of that. And that's not about any specific database. It's all relational databases. But in case of a cache, you just add another server, and now the cache is working. So this is what a cache looks like. It's that easy to use and configure, as you can see. I mean, the only thing that I didn't do is install, which is just a Windows installer, which you know doesn't take that long. So other than that, to configure a 2-node cluster, it took me 5 minutes. And now that I have all this thing configured, I can actually specify this cache name on the applications running on this box. So if I had more client boxes, I would just keep adding them here. In your case, for these two, you'll probably have 8 or 10 of these. So you would add them all, and then once you do, this cache, demo cache, is available there. And then you just go and update your thing. So now that we know what a cache looks like, let me quickly now move to the next topic. So as I said, the easiest way to use the cache is to use it for sessions. How do I do that? I go into my application and oops, not this one. I will go into, and I have this application, so I have this ASP.NET application. What's happening? So I have the ASP.NET application. I would go in and I would open the web.config, and I'll do two things. First, I will go and add the assembly. In case of Encache, that's the assembly that implements the ASP.NET session state provider. So that's how Encache plugs into the ASP.NET framework. Any third-party cache would have to do that. So you just add that line in the assemblies. And secondly, you just go to the sessions tag, and you specify this specific to the distributed cache that you picked. In case of Encache, you just copy this, and there are a couple of things that you need to make sure. First, you need to make sure that the mode is custom. So because custom means third-party storage. And then timeout, make sure it is what you want it to be. And everything else you can keep as default, and just specify cache name here, right there. So it should be just demo cache. As soon as you make this change and you run the application again, or actually as soon as you save this, you know that ASP.NET Worker process recycles. It'll pick up Encache configuration, and suddenly you'll see that every session will be one count. So all those, that count that we were seeing in Encache in this perfmon here. So these would be 540 sessions being stored. And of course, as you add more sessions, it's going to increase the count. So you can, with this little effort, you can immediately give your application a major boost. Same thing goes with the sessions, with the view state, and with the output cache, there's a little bit more configuration involved, but the view state and the session, you can do them in a matter of minutes without any effort, and suddenly the application sees a huge boost. Okay, so now let's move to the application data caching, which is what the bulk of this talk is about. So if you need to use the cache for application data caching, you have to program to its API. And that's because there's no standard API still. So what we did is we picked our API to be as close to the ASP.NET Cache object. And Cache has been around since 2005. So it's like almost 11 and a half years now. But it looks very similar to the ASP.NET Cache object. There's some extra stuff. So let's say you connect to the cache by a cache name, you get a cache handle. Then that cache handle is what you use to do cache.get, get contains, add, insert, remove, and there's an async version of it, which means don't wait for the cache to be updated. And then, of course, when you call the async, then you can specify callback. So your callback gets called in case something goes wrong. Let me show you how this looks like in a visual, in a proper application. So if you were to have this is a standard console application. You would need to reference the assembly of your cache. In case of ncache, it's just these two assemblies, ncache.runtime and ncache.web. You specify the same namespaces here. And then, beginning of the application, which in case of ASP.NET, this would probably be in the global.asax, in the init method or the application start method. But here, let's just, you connect with the cache based on the cache name. And the cache name, as you know, that's how, at least in ncache, that's how cache is recognized. And you get a cache handle, then you create your objects and you do a cache.add. You specify key. This is not a good key. It should have more uniqueness in it. But let's say that you specify key, and here's your value, the actual object. And in this case, ncache is doing this thing called absolute expiration. So let me come to that. So we talked about the application data caching wanting to keep the cache fresh. So if you can't keep the cache fresh, then you're forced to use it for read-only data. So how do you keep the cache fresh? There are more than one way. That's the first way, which is pretty much every cache has it, is called the absolute expiration. This is where you specify how long you want to keep this in the cache. So you say to the cache, I feel comfortable only for 1 minute. That I don't think this data should stay in the cache for more than 1 minute, because I think if it was kept in the cache for more than 1 minute, somebody else is going to update it and the cache will go stale. So you're making an educated guess. Oops, not here. So you're making an educated guess about how long the cache should have your data. And of course, every data that you cache, you should have some sort of expiration for it, pretty much. I mean, some data you can pretty much assume it's never going to be expired, so you can say no expiration. But 99% of the data, or something more than 90% of the data, needs to have expirations. So absolute expiration is what keeps the cache fresh based on an educated guess. There's another expiration called sliding expiration, which its purpose is totally different. Although it uses the same name called expiration, the sliding expiration says, expire this if nobody touches this object for this long, let's say for 10 minutes or 20 minutes. And this is used for more of transient data. So this is used for more of ASP.NET specific data, where you're actually just doing cleanup. You're saying, nobody else needs it anymore. So if a user no longer uses the session for 20 minutes, you're saying this user is logged out anyway, so remove the session. So that's a cleanup expiration. Then absolute expiration, which is a synchronization purpose. The purpose of absolute expiration is synchronization. And again, you can do it, you can expire things in 10 seconds, 15 seconds, 1 minute, 5 minutes, 10 minutes. The most common expiration will probably be a minute or 2 minutes. But there's a problem with expiration. It is that you're making a guess. You're saying, I think it's okay to cache it for this long. But there's no guarantee. In some cases there may be, but in many cases there's no guarantee. What if there's another application that does not have access, that is also accessing the same database, and they go and update that data? There may be some scripts running. So whenever something like that happens, expirations are not sufficient. And that's where you need the cache to have this ability to monitor changes in the database. If you can specify an association between whatever is in the cache versus whatever its corresponding data is in the database, and you can say to the cache, please monitor this data set. If this data set changes, go ahead and remove that item from the cache. Let me show you how that is done. So there's a feature called SQL dependency in ADO.NET that Encache uses, which allows Encache to become a client of your database. And this could be a SQL database, it could be Oracle. And then Encache tells the database to notify it when that data set changes. And that data set is an SQL statement that you specify. Most of the time, it will correspond to whatever, either one or more rows in a table that were used to construct this object that you cached. So for example, where did that go? Here. So if I were to go into the SQL dependency thing, again, same thing. You have a cache handle, and then when you're adding, this cache.add, you're now specifying, in case of Encache, this thing called cache item, which is sort of a structure that contains the value plus some other metadata. One of the metadata that contains is called a SQL cache dependency, which is an Encache class that maps to the ADO.NET SQL cache dependency on the server end. You pass it a connection string, and you pass it a SQL statement. So you say something like, select some columns from the product where the product ID is whatever the value is. So this is one product that you're mapping this to. So you're saying to Encache, use this SQL statement, use this connection string, and monitor that data set, or ask SQL Server to monitor that data set. Now your code, actually this code is running here, right? Because that's where the Encache is. So this then talks to the cache cluster, and the cache server then actually makes the ADO.NET call. And the cache server now talks to the database and becomes a client. And the cache server is the one that that receives the notification. And cache server is the one that actually removes that item from the cache if the database notifies it that this data changed. So by having that feature built in, you suddenly have the flexibility that you can keep data in the cache that you can't even predict when it might change. But you just know that it might change in an unpredictable fashion, so you specify SQL dependency. This is a really, really powerful feature. This is the feature that allows a cache to let you cache transactional data, even when you don't have control over the updates all the time. And because of that, you will cache all sorts of data. Because of that, cache will become actually useful. So, and this can be done in a number of ways. If the underlying database supports database notification, which is the case in case of SQL Server and Oracle, then it will use the SQL dependency or the Oracle dependency feature. If not, then Encache at least has a built-in polling mechanism where it can also let you specify, there's a mechanism where you specify a special table, Encache monitors it, and any rows that change in it, there's a corresponding cache item that it then removes. And a third option is that you actually make cache calls from within a CLR procedure. So whenever data changes, there's a database trigger that calls the procedure, which calls the cache. And that can add data, update data, or remove data from the cache. The only thing with a CLR procedure is that you don't want to make, you want to make async calls. Because whatever you called, it's actually, your database has now become a client of the cache, like backwards, right? So it's trying to update something which will go in here, and then it might get replicated. So all of that's happening within a database transaction, and as you know, database transactions time out fairly quickly. So by making async calls, you can immediately make the cache call and then return the control. So those are the three ways that you can ensure that a cache is kept synchronized with your relational database. Of course, the same logic applies to non-relational. What if your data is in a cloud somewhere, or it's in mainframe and it's, you have a web method call to go and fetch it always? Then in case of Encache at least, you can have a custom dependency feature where your code is registered on the cache cluster. Encache calls it every, let's say, 15 seconds and says, go ahead and please check your data source and see if that data has changed. If it has, fire an event, and then the same logic kicks in. So again, keep the cache fresh is the most important thing in a distributed cache. If you can't keep the cache fresh, it's then very limiting in its use. I'm going to skip some stuff here. There's another feature called read-through and write-through. Read-through is a feature that is, again, a very useful, very powerful feature. It's essentially, again, your code that runs on the cache server. Where is it here? So let's say you implement a read-through interface in case of Encache. Now, read-through, write-through is a concept that is implemented by Encache. It's also implemented by many of the Java players, but on the .NET side, Encache is the only one that has it. So read-through interface essentially is your code. It has a init method, a dispose method, so connect and disconnect, and then load method. It gives you a key, and based on the key, you're supposed to figure out where to go and get the data. And you not only return the data, but you also return some of the metadata, like expirations and other things with it. So what is the value of read-through? So again, this code is something that you implement and you register on the, so it is code that runs here on the cache server. So we've talked about a custom dependency. So if you have a custom data source, that's a code that runs on the database, on the cache server, and the read-through is also something that runs on the cache server. What is the read-through good for? Why should you use a read-through? There are 2 or 3 benefits. Number one, you're consolidating all your persistence code into one place. So if you have multiple applications using the cache, let's say you have multiple applications, they don't have to all implement that code over and over again. So it is kept within the cache server itself. That's the first benefit. Number 2 benefit is that when you expire something, let's say you expire something because of expirations or because of database synchronization, instead of removing that item from the cache, why not just reload it? Because if you remove it, next time the application wants it, it's going to reload it anyway. So you can have the read-through mapped with this and say, where the cache says, okay, if this item expires or if it's out of sync and I need to remove it, I'll instead just call the read-through. So why is it good to call the read-through? I mean, what's the big deal? Why not just reload it by the application? Well, if you have a high traffic application, the chances are that a lot of users are going to be asking for that same data. And your items, you have hundreds of thousands of these items, and they all keep expiring at their own time. So for every time an item expires, you'll have hundreds, if not thousands, of requests hitting the database for the same item. The first one will, and they'll all go and update the cache again. So a lot of unnecessary traffic is going to the database, which if you had a read-through, it would never leave the cache. It'll always stay in the cache, and at some point it'll just get updated. So the traffic to the database never occurs. The second feature is write-through, which works exactly as read-through, except of course it's for writing. So let me show you that. For example, here again you have the init, You have the dispose, but now you have a write, and it gives you the actual object. And then the write could be either add, update, or remove, right? So all three of them are called write. So based on whatever that operation type is, you go and update your database or your data source. Now write through has another benefit. So it has the same benefit as read through in terms of commonality of code. The second benefit that write through has is called write behind, which is that you can update. So there's a feature called write behind where you can update the cache immediately in a synchronous fashion, but the database updates happen in an asynchronous fashion. Why is that a good thing? Well, because anything database is slow. So if you're confident that the database update is going to be done in a timely, it's predictable, why not just queue it up? It gets queued up, and the cache actually performs this operation in the background. That queue also gets replicated to more than one server, so if any one server goes down, the queue is not lost.
So how relevant would this be to in-memory objects in a database or databases that run off of SSDs? If they are also significantly faster, would this then add much value to it or not?
I think everything you have to see in the context of scalability. Whatever is fast, even if it's an in-memory database, it's all on one server. So the more updates are sent, the more reads are sent to it, the more load gets put on the database, the slower it becomes.
Just like a single point of.
That's it. That's the real reason why all of this exists. And then within the context of all of this existing, you get all the additional benefits. That if you had a write behind feature, suddenly your application only has to update the cache in a synchronous fashion. Because once the cache is updated, the cache will take care of the database update in an asynchronous fashion. And that queue has its own optimization. It can do bulk updates. It can replicate. So write behind has the performance, the speed part that you talked about is more relevant to write through and write behind than to the read through. Read through is also something that it might be faster in some cases than application accessing it, but in write behind, it's definitely always faster. Any questions? I've got only a few minutes left. I'm going to talk about one more feature, and then I'll go to the end. So people who are used to doing standalone in-proc, in-memory caching, like ASP.NET Cache Object, when they move to a distributed cache, many of our customers call us and say, you were promising the cache will actually improve my performance. My performance actually went down. Why is that? Can anybody guess? Why does it actually slow down as soon as you move to a distributed cache versus an in-proc cache? Network latency is one. A bigger problem is the serialization and deserialization, which is a huge cost. So what some of the distributed caches do, including Ncache, is they implement this thing called a client cache. Some call it near cache. It's a subset of this cache that is kept within the application server. It may even be in-proc, or it can be out-proc. But a lot of the time it's in-proc. So it gives you the same benefit of a standalone in-proc cache, except that it is synchronized with this. And this is a smaller subset. So let's say this might be 16 gig each server. This might be just 1 gig. And it's a moving window, right? So whatever you're caching is kept, and then as you move on, that the older items either expire or they get evicted, and then new data gets cached. So a client cache gives you the real performance, because it keeps data in an object form within the application process. So if you're fetching it hundreds of times or tens of times, the first time, of course, you need to fetch it from the distributed cache. Maybe the first time you fetch it from the database. It goes to the distributed cache, then goes to the client cache. But once that is done, all further reads are being done within your own heap, which is super fast. So this is a feature that's really, really powerful. You definitely want to take advantage of this. I'm going to now jump to the end, because otherwise I'm not going to. So there are a few things. you need to make sure a distributed cache, just like a database, runs in your data center in your production environment. So it must meet some of the architectural requirements. It must have high availability. It must give data reliability and scalability. So it must do intelligent replication. I'm not going to go into the details of this. You can look in, you can do the research online. For example, if you have multiple data centers, you expect your database to replicate. Why not the cache? You know, why shouldn't the cache also be available in a synchronized fashion across multiple things? So yes, a good cache should be. Now, this is the one I want to end on. If you're doing .NET applications, at this time there are pretty much two options that you have for caching. One is Redis that Microsoft has put on Azure. The other is Encache. On the Java side, as I said, there are a number of players who are pretty good. So I just want to do a really high-level comparison. Encache is the oldest .NET cache. It's been in the market since 2005. It's native .NET. It is also open source, just like Redis. It is also available on Azure and Amazon both. Redis, so there are two versions of Redis. One that is developed by Redis Labs, which only runs on Linux. In fact, Microsoft uses that version in Azure. And the version that Microsoft ported to Windows, they don't even use it themselves, because it's actually, we've heard a lot of complaints from customers. It's not very stable. But outside of Azure, the only version that you have for Windows is the one that Microsoft ported, the MS OpenText. But other than that, if you go to Redis, they'll only give you the Linux version. On Azure itself, there are two differences between Encache and Azure, which is that Encache actually gives you a cache server as a VM. So you can run all that server-side code yourself, monitor things. Redis gives you cache as a service. So the cache is a black box. You only have a very simple API that you call. And the limitation of that is that you don't get all the features that we just talked about. How do you do database synchronization? Read through, write through. Actually, I didn't even go into SQL searching because we didn't have time. So these are the two ways that you can do this. If you want to learn more about this, you can come to our website, and we have a fully detailed comparison document. So if I were to go into Redis versus Encache here, you can see a full-blown document. You can also download it. It's a feature-by-feature comparison based on their documentation and ours, and then you can see which one meets your need. Any questions? That's the end of my talk.
Good job.
Thank you.
So is there any dependency on the .NET Core framework, or can you use it with .NET Core?
Good question. So Encache server supports .NET frameworks. It's 4.0 or later. So, the Encache client by default is .NET framework, of course. We are about to release the .NET Core. So we support ASP.NET Core. So the .NET Core that can run on Linux, we don't support yet because it has limitations. But the .NET Core that runs on ASP.NET framework underneath, only on Windows, and especially ASP.NET Core, Encache will support it. Thank you very much, guys.